Hi everyone, so this is a review for Chapter 11 revision quiz. So based on the responses we have, we will discuss question 2, question 9, question 12, 14, 15, 16, 20, 21, 22. A total of 9 questions. So let's move on to the first question. Question 2 says that you have two steel wires. Okay, steel wires. Then the steel wires are labeled P and Q, and both of them are suspended from the ceiling. Okay, suspended from the ceiling, and each wire is extended by a weight W. So this steel wire P is being extended by weight W. Another steel wire called Q is also extended by the weight W. So if the original length of P and Q are 2L and L respectively, okay, the two lengths are different. The length of P is twice the length of Q, and the extension produced by two wires are the same. Extension produced the same. What is the ratio of the diameter? They ask for diameter of the wire P to the diameter of wire Q. Okay, this seems like quite a long question. So let's write down what we have first. Okay, they mentioned that these two are steel wires. Okay, you might not know why they specifically mentioned these two are steel wires, so let's keep it there first, just in case you don't know. Okay, in case you know, you may write down what the steel wires means. Then you have two wires, which is P and Q, and they are both suspended from the ceiling. So if you have your ceiling, then you will have this steel wire P, and you have another steel wire Q. Steel wire Q is half of steel wire P, something like that. Then both of them, they are suspended or they are extended by the weight W. Okay, something like that. Okay, and the extension produced on the two wires are the same. Okay, let's just write down everything slowly and clearly. Okay, the length of P is 2L. The length of Q is equals to L. Then the extension produced are the same, means by extension at P is equals to extension at Q. So let's just call it E. It's an extension at Q. Because they are the same, I can just call it E. Okay, now they ask for the dimension. They ask diameter, sorry, they ask for the diameter. They ask you to compare diameter P is equals to what of diameter Q. Something like that. Okay, so okay, so this is how are we going to process the question. Okay, first thing is they provide the length and they provide the extension. Okay, now if you want to relate the length and the extension and the weight, okay, now you have one more thing that I didn't mention. The weight is equals to W. The weight of Q is also equals to W. So if you want to relate F, you want to relate E, and you want to relate L, and you want to relate diameter, how do you relate all these things? You relate all of them by using Young's modulus. Okay, of course, this will need to be changed to cross-sectional area. But link them using Young's modulus. So if you want to link them to Young's modulus, means by we have to know what is Young's modulus of P, and you have to know what is Young's modulus of Q. So you might be stuck here. Then you might be thinking, are they the same? Okay, so here's the thing. They mentioned that you have two steel wires. So when they say two steel wires, they already specify the material is steel. Okay, for Young's modulus, it's dependent on the type of material. So in that case, steel wire P and steel wire Q, they are the same material. So they should have the same Young modulus. Okay, So we have all the variables. It's time to just plug everything in. So you say that you know that y of p is equals to y of q. Y is Young's modulus. So change it to F. Stress is F over A. Strain is E over L. Okay, force divided by area is stress. Elongation divided by original length is strain. Okay, so you do it for Q as well. You have your F A, and you have your E L. What am I writing? Okay, now it's a matter of substitution. We substitute everything inside. F, all of them equals to W. L, this one is equals to 2L. Then A, you don't know, we write it as AP first. E is the same, we call it E. And this one is WL over AQ E. So with the situation now, we can cut the W, we can cut the L, and we can cut the E. So we are left with 2 over AP equals to 1 over AQ. So that will mean 2AQ equals to AP. Okay, so that's the situation now. How can we proceed? Well, we want to find diameter, right? Diameter is very much related to the cross-sectional area. Cross-sectional area is pi r squared. But you know, this radius here is equivalent to half of the diameter. So with that said, you can say this is equal to 2 pi dq over 2 square times pi dp over 2 square. So again, we can cross out some stuff. We can cross out the pi. Then we are left with this. Then we do a square root on both sides. So if you do a square root of both sides, you end up with the situation square root 2. Then you have dq over 2. Then you have dp over 2. Again, you cross out both sides, the 2. Then you are left with square root of 2 dq equals to dp. Now they ask for the ratio of diameter of P to diameter of Q. So they want P to Q, so it will be dP over dQ. Then that will be square root 2. So the answer will be square root 2. So that's how you determine the answer. First, you have to be very clear what are you looking for. In this case, you are looking for the diameter. Then see what information you are given. You are being given this thing representing Young's modulus is the same. This thing representing the force exerted is the same. This one representing the length are different by a factor of 2. Then this one representing the extension are the same. So you have all the information. The important thing is piece it together and find the thing that you want at the end. Okay, so that's how you solve a question similar to question 2. Okay, let's move on to the next question. Question 9. Question 9. Below the elastic limit, a force of 10 Newton extends a spring by 40 millimeter. Okay, so you have your force, which is 10 Newton, and extend a spring by 40 mm. So that will be F equals to 10 Newton. Then this extend will be E equals to 40 times 10 to the power of negative 3 meter. Okay, two identical springs are joined in series and stretched to produce an extension of 40 millimeter. So you know that now you have a spring which is joined in series. So means by it's connected together, then now they produce an extension of 40 millimeter. Oh, okay, now they provide two extensions. Let's just call this the new extension maybe. That will clear things out a bit, make things neater. It's also 40 mm. But this time the two springs are joined in series. So if you see two springs are joined in series, what it will look like if it's a vertical spring, okay, it will probably look something like you have a spring which is this length, then you connect it to another spring which has the same length. Okay, so this will be the original length, and you add on another identical spring, so the total length, the new length will be equals to 2L. Okay, that's the new length of this spring because it's joined in series. You might be thinking, does it affect the Young's modulus? Well, probably, but they mention here that the spring is identical. If the spring is identical, means by the length is the same, then you also can say that the cross-sectional area will be the same. The new cross-sectional area will be equal to the old cross-sectional area. Then you can also say that because they are identical, they are made of the same material, so the Young's modulus, the new Young's modulus will be equal to the old Young's modulus. Okay, so with that said, I think we have everything clear already. Now the thing that we want to find is, we want to find the strain energy in the combined spring. Okay, so they are asking for the new strain energy. Okay, so let's zoom out a bit and solve this question. Okay, so a force of 10 Newton and an extension of 40 times 10 to the power of negative 3 meter. Okay, with that said, right, I believe you know what can we find right now. Okay, it says here it's below elastic limit, so that's validating the fact that we are allowed to use this formula to find strain energy. Strain energy will be equals to, okay, strain energy is equals to work done by the external force to stretch the object, in this case the spring. So the work done by the external force to stretch the object, that will be equals to the strain energy inside the spring itself. So that will be half Fe, okay, if it's within proportionality limit. Okay, so with that said, we can find the old strain energy by just substituting all the values inside. So our force is 10 Newton, then our elongation will be 40 times 10 to the power of negative 3. If you multiply all that thing together, you end up with an answer of 0.20 joule. Okay, but that's not what we are finding for. We keep this first. What we are finding is the new strain energy. We are finding the new strain energy. So what do we need to do now is, we want to find the relationship between the new strain energy and the old strain energy. We want to find the relationship now. Okay, so how do we find this? Let's write this whole thing again. We want to find the new one, so it will be U prime equals to half F E. Okay, do you know the new force being exerted? Did they specify anything? No. Can you assume it's the same as the previous one, which is 10 Newton? Cannot. Why you can't assume it's the same? Because the hint is the extension is 40 millimeter. Before that, you have a shorter spring, then the elongation is 40 millimeter, you use 10 Newton. Now you have a longer spring. If your extension is the same, means by actually you use less force actually. But what is the relationship between the new force and the old force? And that's what we need to figure it out. Okay, so force is something we don't know. The new elongation, do we know it? Yes, the new elongation is actually the same as the old elongation. So, okay, let's do this first. Change it to the old elongation because the new elongation is the same as the old elongation. So now F is something that we don't know. Can we change it to something that we know? Yes, most of the time it's changing stuff. If it's involving changing stuff, then you involve this Young's modulus formula. Okay, so this is the formula for Young's modulus. In this case, they are finding something which is in the new situation. So that will be L over AE. Now we know a lot of the things here are the same as last time. So let's change it first. Y, the Young's modulus, is the same as last time. The new force we don't know. Okay, it will be smaller, but we don't know what's the new relationship. The length we know is 2 times of the old length. Then you also know that the area is the same as just now. And the elongation is still the same as well. So if that's it, we can, find the new F prime to be equals to YAE over 2L. Everything is based on the old situation. Y is not Y prime anymore, A is not A prime anymore, E is not E prime anymore, L is also not L prime anymore. So now this is a very suitable equation for us to substitute inside because we have replaced everything from the old, replace everything with prime to everything without prime. So now the new equation will be YAE square over 2L. Okay, so now we want to relate it to the old situation. We want to relate it to the old situation. So how would the old situation looks like? The old situation, sorry for the mess, but you can think of the old situation as, okay, I'll write it here. Sorry, it's a bit untidy. So the old situation is half Fe as well. If you want to change, you can change it based on Y equals to FL over AE. So now if you change in accordance to F, then it becomes YAE over L. So if you substitute this inside, then it will be half YAE squared over L. Okay, with that said, I believe you can see what I'm trying to lead here. You go back to here, take out the things that is related to the old one. Then you'll be left with a half outside. That will mean by, if I proceed a little bit downwards, it mean by this will be equals to, this whole thing here is the old strain energy. So that will mean by the new strain energy is half of this old strain energy. So if it's half of the old strain energy, a bit of calculation left, substitute in the old strain energy, which is 0.20, then we end up with the answer of 0.10 joule. And that's our answer. So our answer will be this. Again, this is a ratio question. For ratio question, the way you do it is flexible. So what I do is I find the old value first. Then I know what kind of relationship I want to build. I want to build a relationship that links the old strain energy, it links the new strain energy to the old strain energy. How do I do that? I derive the new strain energy in all the terms that is related to the old situation. The Y is O, the A is O, the E is O, the L is O. I structure it that way first. Then I find what's the old strain energy, then I factorize it out, and I build a relationship between the new strain energy and the old strain energy. Then it's just a matter of substitution, then I get my answer. The process of doing this finding relationship thing, you can have many ways of doing it, but this is just my way. Okay, feel free to do it your way. Okay, so that's all for question 9. Let's move on to the next question. Question 12 says that the graph shows how the extensions of 4 different wires, okay, they mention clearly the wires are different, and how the extensions vary with tensions. So you have 4 different wires, then under different tension, they will experience different amount of extension. Then the table also shows the original length of the wires and the diameter of the wires. The length and the diameter of the wires, P, Q, R, S. All the wires experience the same stress. So which wire experiences the least strain? They ask for which wire is having the least elongation per unit original length. Okay, so the issue with this question is after spending quite an amount of time thinking about this question, I still can't really make sense of the whole situation. Okay, I might not be able to see the whole picture of this question, but I think this question is slightly illogical. But if you have a better idea, do correct me if I'm wrong. For me, I think this graph is not necessary for this problem. And the next thing is, if I have this graph is not used, then the first sentence will not be relevant to us anymore. Then also I would like to cross out this sentence. All the wires are experiencing the same stress. The sentence itself is a bit weird because they show you a graph where the tension is increasing. Then they tell you they all experience the same stress. So if the tension increase, then the stress will increase. Then all these 4 wires will experience the same stress at different tension. So for P, it has its own amount of tension to have the same stress as Q, as R, and S. Every wire here needs different amount of tension to have the same stress. So actually, I'm a bit puzzled. What does this thing mean? Okay, because the diameter is different. Then same stress, what does it mean you have different diameter? You still need different tension also. So the whole situation is so messy, I cannot figure things out. So I cross out this sentence. So now we are left with the table shows the original length and diameter of each wire. Which wire experiences the least strain? Okay, now we have this sentence, but what I want to do is I want to add on something. Which wire experiences the least strain when being exerted by the same amount of tension? Same amount of tension. So now this will be our situation. Now, okay, if you want to do this question right, you still have to assume one thing. You still have to assume that all 4 wires are made out of the same material. Okay, so I will need to modify a bit the sentence. The table show the original length and diameter of each wire, which are made of the same material. Okay, now you might thinking like, am I creating a new question? It's sort of yes. Okay, I'm creating a new question right now. Okay, so all 4 wires have the same material. All 4 wires, their original length and diameter is being shown in the table. So now I ask which wire experiences the least strain when being exerted by the same amount of tension. Okay, now, okay, I'm basically creating a new question. So for this question, right, you assume that because they are made of the same material, you assume YP is equal to YQ equals to YR is equals to YS. All four of them have the same Young's modulus. Then now you know that Young's modulus is F over A, that's stress, then divide by E over L. Okay, I usually don't remember FL over AE because that's not how the equation comes from. The equation actually comes from F divided by A, which is basically stress, divided by E over L, which is basically strain. See, so these two things divide, only you flip it around, only you form this equation. That's why I don't usually say FL over AE, because I don't have the ability to remember formula. Okay, so now they ask for which one will experience the least strain. So which one will have the smallest E over L? So which one will have the smallest E over L? If you want to have the smallest E over L, okay, this is constant, then this one you can think of it as F over A, this one will be E over L. So if you want to have the smallest E over L, okay, this one is Y, sorry. If your E over L is smallest, that means if you flip it, it will be the biggest. So in that case, you want your stress to be smallest. Okay, so how do you maximize your L over E? To make L over E bigger, you either make L larger or you make elongation smaller. So making L larger means by our choice will be between P and R because their length is larger. Then to make F over A the smallest, it means you either have to increase the area or you decrease the force. But since we already say that our force is fixed, all of them experience the same amount of tension, so we remove this. It means by we want the greatest area. So which one will have the greatest area? I believe the answer is this and this. So wire R fulfill both two conditions, so the answer is R. Okay, it might sound like a weird question right now, yeah, but I think that's the only way I can make sense of it. If you figure out what the question means, then do tell me, okay? I might not be able to see the big picture yet. Okay, so that's for question 12. Okay, question 14. The graph shows how the extension X of a rubber band varies with force F. Okay, again, how the extension X vary with force F. Okay, which of the following is the energy stored in the rubber band when the extension produced is 5 meter? Okay, they ask for when the extension is 5 meter, then they ask for the energy stored in the rubber. So we know that energy stored in the rubber, energy stored in the rubber, it will be equals to the area under the Fx graph, or in this case it's Fe graph. So if we look over here, then if our graph is something like this, if this is F and this is E, if this is our graph, then the area under the graph will be, let's say from until here, then it will be something like this. So this will be our energy stored in the rubber, or you can call it strain energy. Okay, so for the situation now, the slightly interesting thing is they flip the axis. If you see clearly, the force is now the x-axis, whereas the extension is the y-axis. it's a flip. Okay, usually we take the F as the y-axis, we take the E as the x-axis. Now they flip it. So in that case, what it means is our area under the graph is no longer this area anymore. Our area under the graph is actually here. Okay, so this one you have to be very careful. It's because they flip the graph, therefore your area under the graph will be the area towards the y-axis, no longer the x-axis. Okay, so this will be our area under the graph. Well, how do you calculate it? You need integration. Okay, unfortunately you need integration to calculate it. So unfortunately you still haven't learned integration yet, probably soon. So we can't get the answer. But if you look over here, they are not expecting you to give an exact value either. They're expecting you to give range, less than 100 joule, between 100 and 200, or somewhere at 100 or 200 sharp. Okay, so you have the opportunity to give answer which is within a range. So if you are being smart, you know that the only thing that you learn in your syllabus to calculate strain energy is this formula here. U equals to half Fe. But the what do you call it? The requirement for you to use this formula is the force extension graph will have to be a linear graph. Why does it have to be a linear graph? Because if it's a linear graph, then your area under the graph will actually be a triangle. So if it's a triangle, then it will be just half times the x-axis times the y-axis. And in this case, it will be half times the x-axis, which is E, times the y-axis, which is F. And that's how you get this equation, half Fe over here. Okay, so it means by the only thing you can find is if the line looks something like, oops, start definitely. If the line looks like this, well, the line definitely not looks like this, but you know that if the line looks like this, then your area will be more. You have an extra area over here. So it means by if you are able to calculate the area under the graph when the line is like this, you know that it must be less than this area because you have this region here. Okay, this region here, you need to remove it, only you will find the correct work done. But since you cannot find it, you know that it's less than the area under the graph of this pink line. The energy stored in the rubber will be less than the energy stored if the force extension graph looks like this. So if you calculate for this pink line, let's call this the energy stored for the pink line, and be equals to half Fe, and the F will be 40 and your extension will be 5, so it will be 100 joule. So now you know that the U must be the energy, the actual energy here must be less than the U of the pink line, because the line is below this pink line. Okay, it's below this line, and you have an extra area here which you need to remove. So in that case, you can conclude that U, the energy stored in this rubber, must be less than 100 joule. So the answer is less than 100 joule, which is this answer. Okay, so be careful with the axis of the graph and be creative when thinking and imagining a graph. Okay, that's all for question 14. Let's move on to the next question. Okay, question 15. The graph shows the behavior of a wire stretched by an increasing force. So you have an increasing force and it causes the wire to be stretched. The extension produced by the force is E. Okay, because of having this increasing force, you will have an extension called E. Okay, and this is the curve OP shows the variation of E with increasing F. So it means by this line here, OP, this line OP here shows how when the force increase, how the E will change when the force increase. Okay, this is line OP. Then you have another line when the force is decreased slowly after that. The curve PQ represents the variation of E with F. So force decrease means by it's this line here. When the force decrease, this line PQ here is showing how the E will change according to the decrease of F. So we have two sections of the line. One is OP, and if you think of it, OP will go in this direction, it will go up. Then this PQ, this line here will be going down because decreasing forces. Okay, so which of the following shows correctly the area representing the mechanical energy which can be recovered in the process? Okay, so this is quite a conceptual question. So the situation is like this. Let's say, okay, it's slightly not related to this question, but let's think it like this. If you have a spring and you stretch this spring here and you fix this position here, if you stretch a spring, essentially the energy you use to stretch this spring will be stored in this spring here. So let's say you use 100 joule. Okay, let's say you use 100 joule, you input 100 joule to stretch the spring. The thing is, when you let go of the spring, then when you stretch the spring, this 100 joule, where will it go? It will be stored here. This 100 joule will be stored here in the spring. Okay, so when you let go, then this stored energy in the spring will be released back. Okay, and using that, you might be able to drag a ball. You might be able to drag a ball to the left when you let go of the spring. So the energy that is released, the energy that was previously stored, will be released, and it's used to drag the ball to the left. You can think of it like that, how you use the energy stored in the spring. Okay, but now the situation, now we are facing a wire, and as you can see here, this wire is being stretched. Okay, and I would like to bring your attention to this specific point here. You see here, when the force is now back to 0 here, the force at this point is equal to 0, but E is no longer equal to 0. Means by this section here is actually permanent elongation. Means by when you stretch a wire, let's say you stretch it by 5 cm, when you let go, it will get back to near to its original length. But let's say if you stretch it for 5 cm, plastic deformation already, when you let go, it probably contract back 3 cm. So means by you have a permanent elongation of 2 cm. Okay, so this is plastic deformation energy actually. So means by, let's say you pour in an amount of 100 joule right now, and you cause an amount of plastic deformation. What happens actually is some portion of the energy it's stored as the elastic potential energy. Let's say 80 joule. Then some of the energy that you exert to the spring actually release as heat. Okay, it's called internal friction because the atoms slide across each other. So you will waste some amount of energy because of the sliding of the atomic planes across each other. Okay, so this amount of energy here, okay, let me scroll it a bit. This amount of energy here is the amount of energy that you can bring back to do useful work. You can do work using this. Whereas this amount of energy here, this 20 joules as heat, is actually just lost to the surrounding. No, not retrievable anymore. So in this case, we know that the amount of energy left that you can use to do work is less than the amount of energy that you input to stretch the wire, because some amount of energy is released to the surrounding. So with that said, what does it mean is, if you base it on the graph here, then this is the amount of energy you input to stretch the wire. This whole area under the graph here is the amount of energy you use to stretch a wire. But this amount of energy here is lost as heat actually. This amount of energy here is used to overcome the internal friction of the atomic plane. So it's being released to the surrounding. What about the other part, the other portion of this area under the graph here? What is it? What does it mean? It means by when the arrow goes back here, goes back downwards, this energy here that was previously stored in the spring will be released back as for you to do work. Okay, it means by it retract back. The moment it retract back, it release energy, and this energy here can be used to do useful work. Okay, this amount of energy here can be used to do useful work. Okay, so imagine this is like the spring retract back, then you can use it to pull the ball towards that direction. So imagine when you let go of the wire shortens back. Then the process of it shortens back, you can use it to drag something towards the direction where it shortens. So this is amount you can do useful work. This is lost as heat. So you can see that the graph shows the correct area representing the mechanical energy which can be recovered to do useful work. This heat here is not recoverable, it's lost to the surrounding. So the area that we are looking for is actually this area over here. Okay, that's too much to color, but you get the idea. Okay, so the answer is donkey D, this one. Okay, so that's it for question 15. Let's move on to the next question. Question 20. A wire which obeys Hooke's law, means by it's within the proportionality limit, has length L1 when stretched by a force F1. When stretched by a force of F2, the length of the wire becomes L2. So what is the increase in energy stored in the wire? So you have two situations. The first situation is you stretch it with a force of F1, then you get the length of L1. The length of wire will be L1 when you stretch it by a force of F1. Then you move on to situation 2, where if you stretch it with a force of F2, then the length of wire will be measured to be L2. So two different situations. And from the last sentence, increase in energy stored, you can know that F2 is actually larger than F1. And at the same time, if F2 is larger than F1, we can consequently say that L2 will be larger than L1. Okay, because the greater the force being exerted, the greater the amount of stretch. Okay, within the proportionality limit, that's how it works. So I have been thinking about how to find this increase in energy stored. I'm thinking about how to do it in different ways, and I can't really figure out a way to explain it simply using algebra. I think that the easier way to explain the whole situation will be through graph actually. So let's draw a graph. Okay, so here I have a graph that I will label this to be a force against length graph. Okay, now this is not the usual FE graph that we usually see. Usually FE graph, then we know that the line within proportionality limit will be something like this. But we also know that this elongation is actually, if you take the initial length plus the elongation, then you get the final length. And this is the final length that we are drawing here. So we know basically it's just the FE graph, just that for all the E here, you have added it with L0. Means by if the normal FE graph looks like this, what will happen is all points over here, all the points, I will just label 5 points representing all the points will need to be added by this L0 over here. Means by it has to be shifted to the right by an amount of L0. This one will also be shifted to the right by an amount of L0. Shifted to the right by an amount of L0, L0, and L0. Okay, since L0 is a constant value, it means by the graph actually just shift to the right. The whole graph is still the same graph, just that now it's being shifted to the right. The gradient doesn't change, everything is the same. So this is if the situation is FE. Now if you change it to FL, this is what happened. Okay, so to avoid any confusion, I will remove this FE graph. The reason I draw this FE graph is just to show you how I get the FL graph just by knowing how a FE graph looks like. Okay, just remember that this is the situation. L0 is a constant, you add it with the elongation, then you get the final length. So if you are putting FL, just add all the FE graph, all the dots on the FE graph, add it with a constant of L0. Okay, so now I'm going to remove this old graph. Okay, so now this is our FL graph, and we know that when force is equal to 0, that's our original length. Then maybe at a certain force F1, then you have your new length L1. Then in another force, probably F2, then you have another length which is L2. So this is the situation right now. So previously, when a force of F1 is being exerted, if you want to find the energy stored when the force F1 is being exerted, well, it's just the FE graph, the area under the graph usually. So in this case, our area under the graph will be here. Okay, it's the same thing as just now, same thing as the FE graph, just that now it's being shifted to the right. So this is the energy stored when the wire is being stretched by a force of F1, causing an elongation of an amount, causing the final length to be L1. Now, if you further stretch it with a greater force F2, then you store more energy. That's logical. So the amount of energy stored will be this amount shaded by pink here. This will be the amount of energy stored if the force is F2 and the new length is L2. The final length is L2. So I believe you can see this this triangle here represents the O section. This trapezium here represents the increase of energy between the two situations. So what it means is we need to find the area under the graph of this trapezium over here. So let me label clearly where's the trapezium. So this is the trapezium where we need to find the area under the graph. So just a little bit of recall for the area of trapezium. The area will be half times A plus B times H, where A plus B, this is A, this is B, whereas this is H. So this is a trapezium. So if we incorporate this formula here to find the area under the graph, the area under the graph, which is equals to the energy increase in energy stored, A will be the area of the trapezium. So it will be half A plus B. Our A is this, our B is this, B. And our H is this. So with that said, I believe we can form the equation at last. It will be F1 plus F2. Then H will be L2 minus L1. So this is our equation for the increase in energy stored. Okay, let's make it really specific. It's the change in energy. It's the increase in energy stored. So in that case, we can take our answer to be D. This is the correct answer. Okay, so that's a graphical way of approaching this question. An algebraic way will be too complicated, so I think a graphical way will be more intuitive for you to understand. So that's it for question 20. Let's move on to the next question. Okay, question 21. You have the length of an elastic thread that varies with the longitudinal force as shown in the graph. Okay, this is a very similar graph with the previous question. Previous question, the force length graph, it's like this. In the previous question, it looks something like this. Oops, it should be a straight line. Something like this. So now they flip the axis. So if they flip the axis, you should be able to imagine that the graph will look something like this, just like the situation just now. So if the area under the graph just now is here, then now the area under the graph will be here. Okay. This is related to the previous graph that we were discussing in question 20. Okay. So when the force increased from F1 to F2, this is almost the same question, I believe. So the force increased from F1 to F2, and this graph increased from here to here. So the increase in strain energy of the elastic thread is represented by which area over here? Okay, so let's find the strain. Let's find the strain energy in situation 1, and we find the strain energy of situation 2. Then we find the change in, or we find the increase in strain energy. Okay, I will use the yellow line for the first situation. So first situation will be this. Okay, because this is F1, then to be a bit more clear, then this is L naught. So this here will be elongation for situation 1, whereas this here will be the elongation for situation 2. Okay, so the yellow shaded area represents the strain energy in situation 1. For situation 2, label in green, then our strain energy stored will be this amount here. Okay, so I believe you can see very clearly the increase in strain energy will be here. Okay, we don't touch the old one, we just touch the new one. So that will be A3 plus A4. So our answer will be this. Okay, if you see clearly, this is the trapezium that we try to find in the area just now. So this question is similar to question 20. So if you are not sure how this graph is formed, make sure you refer back to question 20 to see how we shift the graph actually. Okay, it's all based on the force elongation graph actually. So that's all for question 21. Let's move on to the next question. Question 22. A load is suspended from the ceiling by a copper wire and a steel wire which have the same original length. So you have copper wire and you have steel wire. They are both used to suspend a load and they have the same original length. So let's be clear, you have a same original length for the steel wire and the copper wire. Let's just equate them to the general L probably. Then a load is suspended, so let's just not assume anything else. So the cross-sectional area of steel wire is twice that of the copper wire. So what it means is the cross-section of the steel wire is twice of the copper wire. Then the Young's modulus of the steel is twice the Young's modulus of the copper. And the tension in the steel wires, which is force in the steel wire, force experienced by the steel wire is Ts, and the force experienced by the copper is Tc. And now they're asking for Ts over Tc. What does it mean? Okay, so to do this, I believe you can see here we have area, we have length, we have Young's modulus, we have forces. All these are pointing to one equation only, and that equation is force divided by area for strain, then divide by E over L for stress, F divided by A for stress, divided by E over L for strain. Okay, so this is the equation for Young's modulus. So with the Young's modulus equation that we have here, we find that the one information that is missing here is the elongation. But I think we can safely assume that the elongation is equals, because let's say they start at the same original length, now they elongate by the same amount here. So the elongation for the copper will be the same as the elongation for the steel. So if that's it, you can add on another information, ES equals to EC, and let's just call it equals to E. Okay, so that's the equation, that's a new relationship that we find out. Okay, just another word, if the elongation is not equal, then you can probably imagine it to be like a slanted load. So in that case, the copper will probably have a longer final length compared to the steel wire. So that would mean by probably they have different amount of elongation. So this one probably experience more elongation, this one less elongation. But that's not the case here. The case here, they have the same elongation. So how do we solve this problem? Again, let's just use the y here. Then if we know that ys, the Young's modulus of steel, is twice the Young's modulus of copper. So now we just substitute everything. Okay, even though we didn't really think through it carefully, but that's the simplest way of doing things for this situation. If you want to compare it in terms of length, then you need to shift the Young's modulus all around. I think that's slightly complicated. Let's just use the original formula, the Young's modulus, and compare the two Young's modulus straight away. Okay, so that will be AS, ES. And you have times 2 of FC, LC, AC, and EC. So now let's just substitute in everything. Fs equals to Ts. Length, they are the same, use the general L. A, let's just substitute with 2AC E is the same for both sides. This one will be 2 times, okay, let's not forget the 2, TC, the length is the same, AC is just AC, E, we replace it with the general E. So now we can cross out AC and E, AC and E, we can cross out L. So now, if we are left with TS over 2 times 2TC. So if we shift things around, that will be TS divided by TC equals to 2 times 2, and that will be equals to 4. So the ratio of TS over TC will be equals to 4. That means by the steel wire here is experiencing a higher amount of tension compared to the copper wire. So why does it have why the steel experience more tension? Because one thing is the steel is having half of the Young's modulus. So means by how should I think through this part? Let's think about the cross-sectional area first. Okay, the steel has more tension because the steel has a greater cross-sectional area. So you need to have greater tension, then match up with greater cross-sectional area, only you have equal stress. Okay, let's just write it out. Stress is equals to F divided by A. So in this case, because you have a larger A for steel, that means you need a larger F. That's what I'm trying to say. Okay. Besides that, Y is equals to stress over strain. Okay. For this, if you increase the if you have a larger Young's modulus, it also means by you need a larger stress. So if it means by you need a larger stress, therefore you need a larger force, because you cannot change the cross-sectional area. That's why this one have a times 2, this one has a times 2, then therefore you have times 4. Okay, just a qualitative relationship to let you see the whole thing. Okay, so that's all for question 22. Okay, no question left. So that's all for chapter 11 revision quiz. Thank you very much.